Okay, today we're going to do the first of two lectures on electronics. Electronics is the branch of study of electricity that deals with the behavior and motion of electrons in a vacuum or in special materials. Now this picture doesn't make a whole lot of sense right now, but after we talk through this, you're going to know what this sort of thing is and what these sorts of things are after we talk through the various aspects of electronics. Next week, we will discuss the specific aspects related to the development of computers and the electronics that are used to develop computers. Now, the phenomenon that's clearly the most important thing is the fact that electricity, that is electrons, can travel through a vacuum. So much like electromagnetic radiation, electricity itself can pass through a vacuum, and this is important to the study of electronics. The foundational device that became very important in electronics was the device known as the vacuum tube. The vacuum tube is a glass tube that contains various electrodes, and these electrodes are then sealed in a vacuum, thus the name vacuum tube. Now, in modern devices, there's very little use of vacuum tubes. These are examples of different vacuum tubes, and if you open up the back of a very old radio or a very old TV set, you'll see vacuum tubes like this. Now, a cathode tube is a tube that has a negative electrode, a cathode, inside a vacuum tube. The positive electrode that's in a vacuum tube is called the anode. Inside the vacuum tube, electrons enter through the cathode, travel across the vacuum to the anode, and then out the tube on the other side. Now this picture is a picture of a device that's used or has been used a lot in the past, and it is called a cathode ray tube. Now, a cathode ray tube, the electrons are emitted. Here's the cathode. It's a negatively charged pole, and electrons come off this cathode and pass through the tube. Now, I showed you that magnetic fields and various other things can cause deflection of these, but it will hit, instead of hitting an anode, it hits the end of a glass tube, and that's what distinguishes a cathode ray tube. You have a cathode ray tube, which is what this pictures, is where a stream of electrons coming off a cathode, the stream of electrodes are called cathode rays, they would, instead of hitting an anode, would hit the end of a glass tube. Now, the end of this glass tube is frequently frosted or coated with a frosted material, and that frosted material, a common example of that frosted material is called phosphor. A TV picture tube, especially in the old days, a TV picture tube is a modified cathode ray tube. So here's the TV picture tube as it used to be made, and here's the cathode, the electrons, and then it is variously deviated by different interventions and fields in this area, and then what shows up is the picture on that area. oscilloscopes, electrocardiogram scopes that you monitor, those are all examples of cathode ray tubes. Now an X-ray tube is simply a cathode ray tube that is modified in such a way as to generate X-rays instead of electrons. And this is an example of a X-ray tube set up to allow for the production of X-rays instead of electrons. Thomas Edison, when he created or invented the fluorescent or incandescent bulb, he noticed that as the incandescent bulb was burning, that the filament would degenerate. And the degeneration of the filament caused black material that was part of the filament to collect in the bottom of the bulb. And anybody that's had a old incandescent light bulb can tell you that the bulb, as it gets older, develops this black deposit on the gravity dependent side of the bulb. Well, what he noticed from that was the fact, what he tried to do is to put in a positively charged electrode inside the bulb, and what would happen is, or what was supposed to happen, was that this positively charged electrode would attract these black particles, and it worked. But what he also found was the fact that the filament radiated electrons, and those electrons would go and attach to or captured by this positively charged electrode. And this emission of electrons was called thermionic emissions. And though he patented the idea of thermionic emissions, he did not realize the full use of such a device. So when current flows, the thing about thermionic emissions is they're one way. In other words, they always are emanated by the filament or the cathode. They come across and they are always collected by the anode, and then there's no opposite direction. This is actually quite important because it guarantees the current flow in one direction and not in the other direction. So this one-way flow is actually extremely important in the development of electronic devices. And so this electronic device, or this, was modified in order to take advantage of this, and this is what's known as a diode. A diode is a vacuum tube, so you have a vacuum in this situation. It contains a single filament electrode, which is the cathode, which emanates or releases the thermionic emission, and a plate or a positively charged anode, and there is a transfer of electricity or electrons across the gap between the two. So this was a simple modification of Edison's first incandescent bulb, and the purpose was not to produce light, but was to produce a one-way flow of electricity. Now, because it's one-way flow, if you're in a place that has alternating current, it cannot flow the other way in this setup. And so what it does, or what it allows you to do, is to transfer or convert alternating current source to a direct current, so that you can only have current flowing in one direction. So the vacuum tube or the diode was a way of changing direct current or alternating current into direct current. Now, the diode was not an efficient way to do this, because the periods of reverse flow ended up being periods or gaps of no flow within the diode. And so what you would have is a staggered flow of electricity as opposed to a steady direct current. And so modifications would be required to prevent this stop-start flow of electricity. Now, one modification of the diode was to place a metallic grid in between the anode plate and the cathode producer of electrons. And since there are now 3 electrodes within the tube, this was called a triode. So a triode is a vacuum tube with 3 electrodes, and the 3rd electrode was a grid that was placed between the anode and the cathode. Now, by doing this, you could charge this grid in a number of ways. If the grid had no charge, then the electrons would flow freely as expected. However, if you put a negative charge in this grid, you could stop the flow of electrons. And so that was the purpose of the triode, was to give you control over the flow of electrons across the gap between the anode and the cathode. The charge on the grid would change and changes the function. If you had a negative charge, you could stop the flow of electrons. If it was neutral, then the flow of electrons would not be affected. So this would act as a gate or a control for the electron flow, and that's useful in many situations. Now you could modify this yet again, this triode, by varying the level of negative charge in the grid. The stronger the negative charge, the less electron flow that could pass, and you could vary the flow of electrons across from the anode to the cathode. And this gave you much better or much more exquisite control of the charge or the flow of electricity across this tube. So because of that, triodes allow for the transmission of things that have varying degrees of intensity, like the human voice, and would also allow to receive radio communications over long distances, because the triode allowed for this significant control of electron flow. It was not just an on-off phenomenon, but it could vary with the volume of the person's voice and also with the pitch of the person's voice, and whether the person had a high voice or low voice. The triode was absolutely essential for the development of modern electronics. Now, this is the advancement from vacuum tubes to something known as semiconductors. Semiconductor is any material that is neither a good conductor of electricity or a good insulator of electricity. In other words, it allows the passage of electricity, but not very well. Semiconductors are frequently made of semi-metals. You recall on the periodic table that about 80 or so % of the materials or elements are metals. About 10 or 15% are non-metals, and then there's a small strip between the two that are called semi-metals, and those materials are used to produce semiconductors. Now, what's generally true of these compounds is that they have, of these elements, is that they have a partially filled valence shell. That is, they'll have somewhere between 3 and 5 electrons in their valence or outer orbit. And that is one of the reasons that they act as a semiconductor, and I'll show you that in a minute. Semiconductors have, as I said, an intermediate number of valence electrons which stay with the atom, like nonmetals, but because there's an intermediate number, they also have holes that allow for the slow transfer of electrons. So if you remember, metals give up their electrons. Non-metals like fluorine and chlorine do not give up their electrons. Semi-metals like silicon do not give up their electrons, but there are spaces where electrons can fall into those spaces and then be transferred across. And because these are not as easy as metals, they are called semiconductors. Now, here's two types of semiconductor. One type is on the left. It's called a P semiconductor because it's missing an electron, and it has a hole where an electron can go in, thus P designation, or positive. And the N semiconductor is a semiconductor that has one extra electron, thus it has a negative charge, and it's a negative or N semiconductor. This is achieved by replacing one of the elements in a semiconductor with another element to facilitate the transfer of electrons. So in the background, you may have, say, silicon, which has 4 outer electrons. And in a P semiconductor, you'll put an element that has 3 electrons. So it has a hole. In a N semiconductor, you would put an element like phosphorus that has an extra electron. And this process, either of these processes, is known as doping, and the purpose of doping is to facilitate the transfer of electrons, either by supplying extra electrons to be transferred or supplying holes where the electrons can be transferred. So as I said, on the right is an N-type semiconductor where the doping material has extra electrons. It's commonly phosphorus, and therefore has extra negatives. Because it has extra negatives, it's called an N-type. The one on the left is called a P-type because the doping material has less electrons, or holes for electrons to fall into, thus it's more positive, and thus called P-type. A material like aluminum or boron would be examples of materials that could be used for that purpose. Now, when you put semiconductors together, you form what's called a semiconductor diode. Remember, a diode in vacuum tubes has a cathode, which is the negative part, produces the electrons, and an anode, which is the positive part. This imitates or mimics that construction by putting a negative N-type of semiconductor on one side and a positive semiconductor on the other side, one corresponding to the cathode, one corresponding to the anode. So the semiconductor diode is formed by bonding together an N-type semiconductor and a P-type semiconductor. And by doing this, you allow for one-way transmission of electrons in this direction from N to P. And it essentially gives you the same effect as you had when you had a diode, which has one-way transfer of electrons. So this mimics what occurs in a vacuum diode. The vacuum diode would have a cathode filament on this side and an anode plate on this side, and you'd have the one-way transfer like this. Now you have the semiconductor material here, N on this side, P on this side, and you have one-way transfer across. Now you actually can have two types. Now these are NPN or PNP, or triode semiconductors. So the triode semiconductor, you notice I have the triode in quotation marks because there aren't actually 3 electrodes there. but it's a device that functions like a triad. So it functions in such a way that you have an anode, a cathode, and then some sort of material in between that allows you for more exquisite control of the flow of electrons across the surface. Another name for a triode semiconductor is a transistor. And obviously, I think the term transistor is probably pretty commonly known amongst people for things like the transistor radio, etc. Now, transistor is just a shortened version of the word transfer resistor. This allows for the transfer of resistance from one portion to another portion of the device. So this is how an NPN semiconductor works. So let's take a look at this. You have what's called a junction resistor, which is a small or plastic or ceramic transistor. You have also the field effect transistor, which is the more common, that's used in computer chips. And again, this P here allows for the control depending on the charge here. You can vary the amount of positive charge in this P by varying the flow of electricity there. When you do that, the ability for this to transfer across here changes depending on whether it's very positively charged or not. Now, just changing the comments in a new direction. Any device that has semiconductors as the principal way in which the flow of electricity is controlled is called a solid state device. It's called solid state because, as opposed to vacuum tube device. So devices used to be either solid state or vacuum tube. Solid state was considered preferred because solid state devices were much more difficult to damage and were much less likely to be broken and were much more reliable. One type of solid state device is called a voltaic cell. Now, there's a very interesting phenomenon that occurs. When you have a device, you put a P-type semiconductor in this device. You coat that P-type semiconductor with a very thin film of N-type material. So you have, on the base, you have a semiconductor that has holes for electrons. And then you coat that on the outside with a semiconductor that has extra electrons. And interestingly, if you shine light on that device, then those electrons that are available are excited and break free, and then because of the P semiconductor being there, they fall into those holes, and that generates a flow of electricity. So it allows for the light to cause a flow of electricity. So here's what that looks like. You have the N-type semiconductor here, the film here, the P semiconductor here. When the light strikes the N semiconductor, it excites these extra electrons and causes them to fall into the holes that are available here. Now you show positive charges here because there has to be a balance of charge exchange, conservation of charge. Then this flow of electricity is then captured and goes through and causes the electric current to occur. And so if you have a bunch of these, you can turn sunlight into the flow of electricity, which is how photovoltaic cells work. And this is the foundational principle behind the solar panels that are on the roofs of houses and so forth. So when light strikes this junction between the N semiconductor and the P semiconductor, the electrons from the N semiconductor are transferred to the P semiconductor, and then that generates the flow of electricity, and that is called the photovoltaic effect. Another type of semiconductor, and I think I've actually mentioned this in the past when we were talking about various ways of producing light, is something known as the light-emitting diode. The light-emitting diode being a term now that makes more sense to you. It's two poles, an anode and a cathode. These are generally constructed of semiconductor material. When you apply electricity to this particular type of diode, when there's a transfer of electricity, it produces light. It's somewhat similar to the reverse of what I showed you in the last slide. In other words, that was the production of electricity by shining light on semiconductors. This is the opposite, where you apply a current to a diode, semiconductor diode, and it produces light energy in the process of the transfer of electricity. And so this is what it looks like. And what you have is the cathode lead, the electricity comes in through here, enters into the N-type semiconductor, and then travels across and out the anode lead, and in the process of that, light is then emitted. And there's enormous numbers of various ways in which this is used. The lights on your refrigerator or on your oven, on your microwave, many of those are light emitting diodes that count down time and so forth. Another way in which semiconductors are used is a semiconductor laser. Now, the semiconductor laser is somewhat like a light emitting diode, but a much more powerful process. So when current is applied across the N-P junction, in certain types of materials, there is the generation of a crimson laser beam. And so this is what that looks like. You have, again, current and the current is flowing in this direction from N to P, from negative to positive. And in certain constructions, when you do that, there's the production of crimson laser light. Now this has absolutely revolutionized the electronic world. This took the place of the diode, the diode is or the triode is making electronics possible. This is what's known as an integrated circuit. Now, an integrated circuit is a device, a single piece of material, which is made generally of semiconducting material, and it allows for the application of an entire electric circuit in this one single piece of material. And so that is what's known as a integrated circuit. Now, it has the advantage of being a very small size and also very small weight, and so you can pack a huge number of circuits in a very small area. The original computers that were made generally took up several rooms because of the circuits were all vacuum tubes and gross wiring. And then a lot of the advancements from that point were due to the fact of being able to make smaller and smaller circuits first using semiconductors, and then ultimately using integrated circuits. Now, integrated circuits are made by taking semiconductor raw materials, and actually what they do is they produce a fairly long rod of this stuff, or bar. It's a round, it can be square. And then they cut this in very thin wafers. The materials, using the raw materials, they also put light sensitive materials in this. And what they do is they shine pictures of the circuits that they want. And the light sensitive material imprints the pictures that are shown of the circuit and imprints that on the semiconductor raw material. And so you end up with small squares or small circles, wafers, that have the circuit in them. And so this is actually produced by taking light sensitive material, and they shine a picture of this on this wafer, and they do that several times over a period of time, and they ultimately end up with a little square, very thin little square that has this outline, and then they can attach electricity to one or the other ends, because the picture is set up in such a way as they know what they have to attach to each of these ends in order to complete the circuit that they want to complete. This is truly a marvel of modern technology, to be able to make these circuits this way. And this kind of advancement in technology is what allowed for the advancement of the various devices that we have, such as our smartphones and our computers and our various other devices. So what are the true benefits of these integrated circuits? Well, integrated circuits, because of their the way they're done, they actually are easier and much more cost effective to make. You can make integrated circuit in a very short period of time. Integrated circuits are much more reliable. Once they're in place, there's not a lot of jostling and not a lot of interference, and so the wiring does not get disrupted by trauma or various other problems. Also, if an integrated circuit is damaged, you can take another one that's exactly the same, pull the first one out and put the other one in, and it is fixed. It is much easier to repair. And then probably the most important part is the fact that these are extremely small and extremely light. And this allows for the packing of an enormous number of circuits in a very small thing like a cellular phone or a computer. Now on the left, you have actually what would be a very large integrated circuit. This would be plugged in. This could represent memory chip or something of that nature. You plug that in, and there would be this huge amount of area in which to have various circuits. If that were to become damaged, you could just unplug that and plug another one in that's exactly the same. On the right is the way in which these integrated circuits are made. There's various techniques that are used, but a lot of them have to do with what you see on the bottom there, the photolithography, which is using light to imprint these integrated circuits. And so the next lecture next week will be on the integration of these electronics into the computer and how computers are set up. And that'll finish our 2 lectures on electronics. After that, I'm still thinking about what sort of lecture to give. I've been thinking about possibly lecturing on the origin of the universe and the various theories behind the origin of the universe. So make sure you bring your questions to the class about this, and we'll go from there. Thank you very much.